Today, I'm going to demonstrate the voltage and current relationships that we are going to encounter when we're working with resistive and inductive series circuits. Using a lav volt workstation, I have built a resistive and inductive series circuit, but what I've done is instead of using analog meters, I'm using this data acquisition module, using the software that comes with it that's preloaded on our computer. It is going to act like a virtual oscilloscope. What I'm going to do is show you, my viewer, how does the voltage and current waveform react in different points of a circuit. According to the popular theory, when we have a resistive component in a circuit, the voltage and current are in phase with one another. Over here, the inductive load module, according to the popular theory, inductors oppose a change of current, and that is going to create a 90-degree phase angle difference between the voltage and the current waveform. We're going to look at it through the lens of an oscilloscope. As well, we're going to look at the circuit in its entirety, and we're going to determine in the calculations of angle theta what should be the total phase angle difference between the voltage and current for the entire circuit. So I'm going to reset the camera so that we can have a really good look at what's going to happen here on my display. The diagram you have before you is to demonstrate at which points inside the circuit that we are going to be capturing the information. You can see we have a single amp meter, but because this is a series circuit, we're going to be measuring the voltage drop across the power supply, as well as the voltage drop across the resistive load module and the voltage drop across the inductive load module. So here we are at the workstation. I've got the display set up, and all I need to do now is to turn on the power. So let's do that. I'm energizing the circuit, and what we can see is currently the waveform for the current. The current, it wouldn't matter where I measured it in the circuit, that waveform would be the same. What I'm going to do first off is I'm going to turn on the channel that is reading the voltage across the resistive load module. According to theory, they're supposed to be in phase. So let's do that right now. I'm going to go to channel 3 and let's turn it on. Now I'm going to freeze the screen so we can get a better look at what's going on. Now, if I use this cursor, what we can see right here in the green line, is that the voltage and current waveform. So the pale blue waveform represents the current in the circuit, and you'll see it says down here channel 2, A for amperes, and for channel 3 we have this purple waveform. It represents the voltage across that load module. According to our text, voltage and current are supposed to be in phase. And what they mean by that is that right at this point, when we're going into the negative alternation, the voltage and current waveform, there's no phase angle difference. They start at the exact same point. They rise in unison. They both peak in unison, and then they collapse in unison. They cross over the center line of 0, because this is time base, and then they rise again in unison, peak, and collapse in complete unison. So this is what they mean by zero phase angle difference. Now let's turn on channel 4. Now channel 4 is taking a reading right across the inductive load module. Now I've got to update this, and I'm going to freeze the screen. Well, that's pretty good. So what do we see? Well, according to our theory, there should be about 90 degrees of phase angle difference between the current waveform and the voltage waveform. Now, in a series circuit, the current waveform is stationary. And because of that fact, we have to say, because this sentence is grammatically correct, that the voltage is going to lead the current. because current can't lead or lag anything. It's stationary, and it is the voltage waveform that changes in relation to the stationary current waveform. And if I take my green cursor and I highlight this, you'll see that the peak is right about there. If I was to count the divisions and divide it by 2, I'd end up right about here. Now you'll notice there's a slight discrepancy here. The discrepancy is due to the fact that these inductors are not perfect, that the inductors have a certain amount of resistance. It's fairly small in comparison to the value of inductive reactance, but there is some resistance there. And for that reason alone, it accounts for why are we not exactly 90 degrees out of phase. It's because we have a little bit of resistance. So these are not perfect inductors. Now, let's move on to the entire circuit. And there we have it. This is a circuit we have built based off of another video where we built an RL series circuit. And in that video, we calculated that angle theta was about 56 degrees. If I take this cursor and, we're moving things here. I can take the current waveform, and I'm trying to put it equally in the middle here because this represents 180 degrees. The center section represents 90. The fact is that the distance from here to here, or conversely from here to here, is supposed to represent 56 degrees. So if I count the divisions, so there's 5 degrees, 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees. So if I count 10, 20, 30, 40, 50, and it's slightly more than half. So this is the reason why we will calculate angle theta for an entire circuit, is that I can actually count to verify, did I build the circuit correctly? And I can verify my work. This is quite handy, but without having calculated angle theta, this exercise becomes pointless. Also, if you'll note, let's see if I can't move. No, I can't. We'll use this as a reference. You notice where the current starts and it strikes and it intersects with this line. If I follow the line up, you'll notice that the voltage waveform is at the top and it's in its positive alternation. This indicates then that the voltage is actually leading the current by the 56 degrees that was calculated previously. If this voltage waveform was down here in the negative alternation, we would then be able to say the voltage is lagging. But that's not what we're looking at here. We're seeing at this point, I take and I follow this line straight up, that is a voltage waveform, and it's also confirmed down here. It says channel 1 V. So that's the voltage. Now we can see that I've got all three waveforms for the voltage across the resistor, the voltage across the inductive load bank, as well as the input voltage to the entire circuit. They're all overlaid, and what we can do is examine the relationship between all of them and the current. Now if I put the current smack dab in the middle, we can use as a reference that the current and the voltage across the resistive load module are completely in sync with one another, or in unison. That the voltage in purple here and the current are almost 90 degrees out of phase with one another. Why are they not perfectly 90 degrees? There's a small amount of resistance in the inductors. And the goal represents the entire circuit overall. I'm hoping you found this helpful and it helped to clarify certain issues that you may have with understanding how voltage and current can behave in a resistive and inductive series circuit.